So let's go to the next page. Okay, it says polygon ABC has the coordinates 4, 4, 4, 16, and 12, 4. It was dilated by a scale factor of 1.5. Remember, scale factor, this is the number you multiply by. Oh, let's do this. My M looks a little weird. Okay, so scale factor 1.5. 1.5 is larger than 1, so I imagine it's going to be an enlargement. And let's see. Represent the transformation algebraically and graph the image. So let's go ahead and represent this. So our original one is xy. And we are going to transform it we're going to dilate it by a scale factor of 1.5. So that means 1.5 times the x's. Let me draw that a little bit better. And then 1.5 times the y's. Okay, so it tells us what they are. So A, B, C. So I'm going to label them actually with blue. So A was that one, B was this one, and C was this one. Oh, this might be incredibly large. Yeah, I didn't realize this thing's going to be humongous. 8. So let's do. You know what? Let's just go with it. It's gonna look beautiful. It's gonna be beautiful. All right. So let's take A, B, and C. I'm gonna write A and a 4, which is 4, 4, and we'll take B, which is 4, 16. And we'll take C, which is 12, 4. And we are going to dilate all of these. Instead of writing it, I'm just going to put times 1.5, like that. And then I will get A prime, B prime, and C prime. Okay, so 4 times 1.5 is 6. 4 times 1.5 is 6 again. So I'm going to write 6, 6. This is A prime. 4 times, oh, same thing, 6. Okay, now this is where it's going to start to get out of control. 16 times 1.5 is, let's see, half of 16 is 8, so it's 24. Okay, that's going to be like way up there. We'll graph that one later. 12, 4. So 12 times 1.5 is 18. At least that's somewhat more reasonable, I think. Oh, because it's over here, actually. Okay, and then 4 times 1.5 is 6. So we're going to do our best over here. So that's 18, 6, 17, 18, 6. Something like that, right? Now, the ridiculous thing is that this thing goes to 624. B prime is at 624. So, I'm going to, it's somewhere up here. I'm going to, like, I don't know, like, somewhat ridiculous. So I'm going, it's up, well, it's hard to zoom into that part, so I might have to zoom out in a second. But I'm drawing this point, if I can get it there. Okay, and oh, there we go. So let me see if there's a way I can zoom out a little bit. Okay, maybe more. Okay. I think that's as much as I can do. But you can see how this thing's ridiculous. It's just like, it's like, bam, I want you to write, I want you to show the arrow, right? Show the arrow. Like, bam, times 1.5. And then I want you to write that this is the, I'll write it in red, actually, so you can see it better. I want you to be like, bam, times 1.5, and then I want you labeling this the dilation. Okay, I'm going to zoom back in. Okay, so I can represent the dilation. This is a dilation. I'll keep it in red. I can represent the dilation algebraically using the coordinates 1.5x and 1.5y. The dilation will be, okay, so we got larger, right? Will be larger. Therefore, the side lengths will, remember, congruent means equal. The side lengths are congruent or not congruent? They're not congruent because they're not equal anymore. They've changed sides. The angle measures. Let's look at these angle measures. If you notice, this is a right angle, 90 degrees. 90 degrees. If this is, let's say, like 30 degrees or something, that top one is still 30 degrees. If this is 60, then this is still like 60. Like, the angles don't change when you get larger or smaller. They don't change the amount they open up. They just go further with the lengths. So the angle measures are still congruent. And the orientation is the one. So I want you to think about this as whether you see the front or back. Front / back. When we blow this thing up, we're still looking at the front, so the orientation is the same. You'll get used to that. We're going to do that with every transformation we will be doing. Okay, so polygon A, B, C is shown below. I'm going to try, no, I don't want to zoom in too much. Yeah, I can on this one. Okay, so let me get that right. Okay, so polygon ABC is shown below. It's dilated by a scale factor of 1/3. Okay, so let's go ahead and do that. So let's represent that. We had x, y. And then we dilated by a scale factor of 1/3. So that means we took 1/3, we multiplied it by the x, so the x is times 1/3. And we took the y's and we multiplied by 1/3. Oh man, I don't think I was doing that bad. And then I look back. It's this parenthesis x and 1/3 y. Okay, cool. So it doesn't tell us the locations of the vertices of A, B, and C. So let's just go ahead and write those. So this one is -3, 6. This one is 6, 0, not 0, 6, 6, 0. And this is -6, -6. Okay. Let's go ahead and write them down. Let's see. So A was negative, is up here, so -3, 6. B is 6, 0. And C is -6, -6. And we transformed all these. By dilating by a scale factor of 1/3. I can make that a little bit better. And I get, let's see, so negative times, well, this is still going to be negative. Negative times positive is negative. 1/3 of 3 is 1. If you need to use calculator, use calculator. 6 times 1/3, or 6 times 1/3 is 6 times 1 is 6. Whatever 3 is 2. And 6 times 1, oh, it's the same thing. So that's 2. And then 0 times anything was 0. Negative times a positive is a negative. 6 times 1 is 6 over 3 is 2. And it's the same thing. So I just need to label these A prime, B prime, C prime. All right, let's graph these bad boys. Negative 1, 2. Negative 1, 2 is A prime. 2, 0 is B prime. And negative 2 is C prime. Cool. 2. And then I need to label that this is the dilation. And we went from this large one to this small one by multiplying by 1/3. Let me write that a little bit better. Oh man, now I can't even understand this word I wrote right here. Read it. And then we went like this by multiplying by 1/3. All right, let's do some statement. Okay, so I can represent the dilation, the change in size, algebraically using the coordinates 1/3 x and 1/3 y. The dilation will be smaller, like we got small, you can see, like bam, smaller. Because we multiply by a number less than 1, right? Less than, like, well, between 0 and positive 1. So like 0.5, 0.6, 1/2, 2/3, like you're going to get smaller. And therefore, the side lengths are not congruent. Remember, like side lengths, congruent means same size. Not congruent, it's not the same size. The angle measures, the angles. Remember, the angles, when you get bigger or smaller, don't change. Like if this was 60 degrees for whatever reason, then this would still be 60. It just goes like the sides just make it like up here maybe smaller, but like that 60 degrees, that's still 60 degrees. Ooh, that was bad. And so the angle measures are congruent when you dilate. And the orientation, so remember, orientation is whether we're looking at the front or the back. We are still looking at the front. The only time where we're not going to be looking at the front is if we like flip the shape, but we didn't flip the shape, okay? So the orientation is the same. Awesome. So that's it. Thank you.